I am deeply honored to have the privilege to present the Peck Award to John Wolosick. I have admired John for the past 23 years, since I've known him for his incredible role in the deep foundations industry. In thinking about John and his numerous contributions to the geo profession, 8 words come to mind. And this is us 2010 and 2023. Innovator. John solves technical and construction challenges and has engineered ways to build foundations on extremely challenging projects. I was brought into the micropile community as a young engineer. My first summer internship was as a 19-year-old freshman at Penn State University, and for my summer job, I was inspecting the installation of micropiles for a parking garage. At that time, I learned a lot about the character of the contractors in the geo profession. Not only in the profession, but in micropile technology in particular. A big reason for this is the International Society for Micropiles, ISM, a consortium of micropile designers, contractors, and suppliers who come together about every 2 years in different countries to promote micropile technology. John is a key figure in ISM. Mentor. John is incredibly generous with his time and has never refused to stop and answer questions I have had. He has taken an interest in my career and offered advice and pointed me towards new opportunities. Pioneer. If someone's thinking about putting micropiles on the moon or any other uncharted territory, you better call John first. I'm chair of the Micropile Committee for DFI, a position John also held, and one day Teresa Engler, executive director of DFI, called me saying there had been an inquiry on the website about what the longest micropiles ever installed were. Yes, I called John, and yes, he had installed them in Hawaii, over 200 feet. Storyteller. John tells the most captivating stories, as you'll soon see. You can absolutely picture in vivid detail what is happening. He has such a talent for painting a picture. It doesn't matter if I've heard the story a couple times, I still want to hear it again. People even request certain stories. Engineer. This is an obvious one, but John is a PE and an SE, and he can build and troubleshoot challenging construction sites on the fly when things are not going according to plan. Teacher. So many times I've seen John taking the time to explain a micropile or engineering concept. Champion. When I was putting together a team to propose on writing the new GEC 16 Micropile Design and Construction Manual for the FHWA, I knew we had to include John or risk losing the project. He's so passionate and enthusiastic about micropile technology. And leader. John is truly a leader in the geo profession. I am honored to present him with the Peck Medal as our 2025 Peck Lecturer.
That was beautiful. Thank you. You want your phone? I'm sorry. Oh, I'm sorry. Sorry. Sure.
All right, right here. Good, hold that one more. Thank you.
Thank you. All right. Okay, great. Thank you. Oh, yeah. Okay. Thank you very much, Helen. That was beautiful. Choked me up a little bit. I'm really honored to be here today and to be selected to do the Peck Lecture. Ralph Peck was a hero of mine and taught at the university where I attended, and so he's obviously a huge figure in the business and one of my heroes. Ralph Peck taught at the University of Illinois for 3 decades. Here are a couple of pictures of him in Illinois that I was able to come up with. Unfortunately, he retired from the university when I was a freshman, but luckily he came back almost every semester I was in school, gave lectures, often about case histories, the Teton Dam had just failed, and he was the prime consultant on the Teton Dam, so I learned dam, and so we learned a lot about that. He was an eminent consultant and geotechnical engineer, and he grew up as a field engineer working on the Chicago subway and was the eyes and ears of Carl Terzaghi. That collaboration led to them writing the famous book, Soil Mechanics and Engineering Practice. And then that book was then later updated within the last decade or so with the help of Reza Mesri, Terzaghi, Peck, and Mesri. So many of you probably own that book. You have it on your shelf and use it as a reference. When Peck was at Illinois, he developed a course which at that time was called CE 484, and it was Geotechnical Case Histories. So he has always been and always was very passionate about case histories. I took that course from Herb Ireland, who's shown on the lower right there, who was also my advisor in school. And it was a famous course at Illinois because you had about a week per case history, and you had to summarize the case history on one page. And at that time, I'm old enough where word processors didn't exist. And so we had typewriters, and everybody would type, and sometimes, the notes would go around the side to try to, they didn't care what it looked like as long as your thoughts were clear. And so I took that course. It was great. On the upper right is a picture of Dr. Peck with Walter Hansen, who was the engineer that wrote Peck, Hansen, and Thornburn, another really good text that many of you probably have. And Walt Hansen is from my hometown, Springfield, Illinois, and Hansen Engineers is his legacy, which is a really well-respected engineering firm, but where I grew up. In 1990, I presented a paper with Seth Perlman at the 1990 Earth Retaining Structures course, and the keynote was Ralph Peck. And so his paper was the first one in the geotechnical specialty publication, and it just so happened that we were on the same plane leaving New York, and I had a young engineer with me, Mike Randolph, and he said, "Hey, there's Dr. Peck, I want to take the book and get his signature." So he took my book, and what you're looking at there on the right-hand side is with best wishes, Ralph B. Peck, 1990. So it's one of my cherished items, having his signature. And then, once again, the picture at the bottom with Reza Mesri, who I took soil mechanics from when I was at Illinois. So happy to be here, excited about being part of the Peck legacy, etc. So I wanted to thank very much also the Geo-Institute and the Board of Governors for this selection. When I got the call, they said, well, one thing we want is we don't want you to talk about something you've already talked about before. So guilty as charged, I might say. But fortunately, I had a couple of pretty cool projects that were current and was able to talk about. They're not micropile projects. They're earth retaining structures projects. My other passion, and in particular, soil nailing. I love soil nailing. And I would also like to dedicate this talk to some friends and coworkers that I've known, learned from, and loved for many years, and that is the Triplett family. Ron Triplett, who I've worked with for 40 years. His brother Deke, who was a superintendent, 30 years with him, and then Deke's wife Sandy was my assistant for 20 years. And she was a big reason why my publications came out on time and without typos, and were well organized. She was a former math teacher and very detail oriented. And then I'd also like to dedicate it to Jim Jones, who was a cousin of the Triplets. And I've worked with Jim since he was 20, which I think is about 38 years. And he is an excellent guy in innovation and soil nailing, and it had a lot to do with both of these projects that I'm going to talk about. And so the theme of my lecture, I've got a double theme here. The first one is construction. Okay, now I love design, don't get me wrong, but today we're going to talk about construction. And I really get enthusiastic about construction. I was a field engineer for 12 years. And after working in design for about 8 years, to finally get out in the field and really experience building things was an eye-opener to me and something that I really enjoy. So the two projects that I'm going to talk about are both big soil nailing jobs that have taken place since 2021, and one is still ongoing. And the first one is a project in Natchez, Mississippi, for the U.S. Army Corps of Engineers at the Natchez National Cemetery. And it's a big soil nail wall. If you look in the lower left-hand corner there, you can see it wrapping around the cemetery on the bluff of the Mississippi River. It's almost 1,300 feet long. It gets as tall as 48 feet. The average height's about 31.5 feet. 40,000 square feet of area. And we were the general contractor for the project for the U.S. Army Corps of Engineers. The second project is still actually ongoing. The final work hasn't been done because it was shut down by winter, and that is the Teton Pass landslide, also called by Wyoming Department of Transportation the Big Fill slide, which occurred in June of last year. And we're going to talk a lot about that. It's a very tall wall, 110 feet in the corner. It's 60,000 square feet. And we worked as a subcontractor on this project to the general contractor Ames Construction out of Minneapolis. But not only does it have soil nailing, but it also has a really large scope of micropiles as shear pins in the bottom of the fix. So, Natchez Cemetery. Another theme for my topic is repeat business, repeat clients. And so this was the third project we had done in Natchez for the Army Corps of Engineers. And the previous ones were a long time ago. They were quite early, as I'll show you here. And if you've never been to Natchez, you should really take the time to go. It's really New Orleans in Mississippi. It's a very fun, lively town with a nightlife. It's an eclectic town with a lot of artists and really great food. And I've spent a lot of time in Natchez, and I really love it there. But this is a national cemetery on the north side of the city. The city you see here on the the left side is down a little lower. And as you work your way up the river, the Mississippi River, that is the cemetery. That site is located there because it was the location of two really major Civil War battles where a lot of people lost their lives. And that's what the cemetery started at. And it's still open to all of the branches of the armed services, and there were interments going on the whole time we were there. So a really interesting place. So the repeat business, just for fun here, are two or actually three different projects that we did in Natchez between 1997 and 2001. And the first one on your right there is the Clifton Avenue, Learned's Mill Road project. It was a 74-foot high soil nail wall with a 37-foot high MSE wall built with lightweight aggregate fill. Basically, the bluff had fallen away, taken the road with it, and there's a big house in the middle that's on the National Register of Historic Places that was built by Mr. Learned, who owned a sawmill down at the river here, at that location, excuse me. And The lady who lived there, I actually told about this story in one of Brad's field trips, Maggie Berkeley, but she couldn't get residential house insurance because the bluff was 3 feet away from her front steps. And so we came up with this concept to actually replace that area with the MSE wall, and there were some tieback anchors involved as well. And then in 2000, 2001, we did the Natchez Under the Hill and Rosalie Mansion at Silver Street. It's the wall you see on your left there, which is also a pretty tall wall, about 45 feet high, 50 in some areas, and a row of deep tieback anchors. So working for the same folks again for the Corps of Engineers. The first contract was actually for the City of Natchez, and then the second 2 contracts were for the Corps. So the main erosion event that occurred at the cemetery was in 2021. It was a wet time, and the bluff was adjacent to this site. There was an MSE wall there and a pavilion, and during a particularly rainy time, this big slide occurred. They tried to save the MSE wall, but unfortunately it was severely damaged. And they did the things that you're supposed to do. You cover everything up with plastic and try to keep the water out, etc. But the wall was pretty much toast. And that got the ball rolling for a larger scope of repair all around the bluff where they had incipient problems that looked a lot like this. So the geotechnical conditions in this area along the Mississippi River, it is very similar all the way up to Vicksburg, is you have this thick layer of loess. Some people call it loess. The German word I think is Lurs, and it's for loose, but it's a wind-blown silt that has a clay and sand fraction and also has a calcareous binder that kind of sticks it together. And it exists in vertical bluffs very easily. In fact, if you try to put it on a 2-to-1 slope, if you cut into it, it will erode severely. And so they actually cut it vertically if they're going to make a cut. They'll come down 10 feet, a little bench, cut 10 feet, etc. But it does erode over time. It is an erodible material. So this slide was in the loess, which is the Vicksburg Formation, and then below that is the Natchez Formation, which has an alternating sand, dense sand and clay layers that makes a really good material to bond pre-stressed anchors into. And so when we first started working there in Natchez in the mid-90s, we were doing tieback walls along Silver Street and learned about good bond materials in this sand. But also, the original idea came from a guy named Eddie Templeton at Burns Cooley Dennis in Jackson, Mississippi, and he called up and said, "Hey, I saw you do a presentation on soil nailing. I wonder if we could do it in loess." And I was familiar with the material, and I thought, I don't know. We'll have to see. We'll have to run some tests. And so we did some tests. You get very low bonds, and I'm going to talk in U.S. units here, like on the order of 5 pounds per square inch of bond to a grouted nail, so that's really low. So in most of these cases, and on this project I'm going to talk about, we had to drill 10-inch diameter holes to get proper bond for the soil nailing, but it works great when you do that. Here's a plan view of the location. Like I said before, it's 1,270 linear feet, pretty long, almost quarter mile. And so the erosion area that was the slip that I showed in the picture is in the center portion here. The cemetery is on the bottom of the slide, and the riverside is on the top of the slide. So it meanders around the cemetery, actually goes around some residential houses on the side that were threatened as well. And the maximum height, as I mentioned before, is 48 feet, average height 31.5 feet. And I'm not going to talk a lot about design, but let me just mention a few things. We The consultant for the Army Corps of Engineers in this project, who wrote the report and did the borings, was Burns Cooley Dennis out of Jackson, Mississippi. And the concept that we have for this bluff stabilization is basically just to remove a big chunk of the loess at the top, because your driving forces come from the upper side of your landslide typically, or your slope instability. And so these are just some sections. This was a design build project. The design was done by our engineering staff out of our Nashville office. And this is an internal stability check and an external stability, global stability check that shows the plan for putting in the soil nails. But the thing about doing this type of job, and if you noticed and saw in the pictures and in my references there, the thing about doing this type of soil nailing is you can get really great stability numbers using soil nailing, but they have to be really long. And they're closely spaced. They may be 5 by 5, 6 by 6 feet or whatever. And so the lesson we learned early on in the early jobs was you can soil nail and get a decent internal stability, but to get that external global stability, what you do is you include an anchor, a deep anchor. These anchors were 150 to 180 feet long. They were big, about 250,000 pounds, 250 kips each. And so that combination of the two works very nicely for an extremely economic design and an efficient design. This is just another section here that shows internal at a different section, internal stability and external stability. And the external, we're throwing in a pseudo-seismic acceleration specified in the specs by the Corps, and checking our factors of safety. So that's the design. So that's the concept, you know, is to soil nail for the 40 or so foot sections. It was 7 rows of soil nails. They were 40 to 50 feet long on a grid pattern of 6 by 6 feet or 6 by 7.5 feet horizontal spacings, and then a single row at the bottom of the wall of deep tieback anchors, you know, 150 to 180 feet long. And what we did was we came up with a concept, in this case, to shotcrete a big whale beam, a reaction beam at the bottom that would support the loading from these big post-tension anchors that provide us with our global stability. And so the tricky part about doing this soil nailing is, you know, the failure comes right up to the surface, and you'd like to soil nail if you can from the ground, but if you don't have enough room to make a bench, you have to reach over, et cetera. And so it makes it better, and it makes your soil nailing work better if you're on a batter. The forces work out to be much less, but you really can't batter if you've got a constraint at the top of either a structure or the room to do it. And so what we did here was we went vertical for the first 2 lifts to give us enough room to get a bench in, and that way our people can work on foot. And then as we went down, we had enough room to get a drill and personnel in at those lower levels. So vertical for the first 2 rows, and then we battered the wall out at 20 degrees, and that really decreases the forces required to get the proper factor of safety. So we separated our work area from the cemetery. As you see here, the access road, we were right adjacent to the graves in this area. And when the MSE wall failed, it also damaged severely an interment pavilion that was located there. And that had to be demolished as part of the project. And then we also had an additional scope of building a new MSE wall, but this pavilion was not replaced because there really wasn't room for it anymore. We actually stepped back into where the footprint of that pavilion was in plan view. So starting off, you see here we are reaching over ourselves here. This is a drill mast attached to a track hoe. It's made by a company called Word in Virginia, I believe. And so we're drilling back under ourselves doing the soil nails. These holes pretty much stayed open. We did have to case some of them, and this drill is capable of doing that. And these are not hollow bars, they're solid bars. They're number 8, 1-inch diameter, epoxy coated all thread bars. And so here you see the soil nails being drilled in, and then the shotcrete installed lift by lift. This is a top-down process, which is very economical. Instead of building the wall from the bottom up, we build it from the top down as we go down. We ran a series of pull-out tests on every row that we did to confirm the capacities that we assumed in the initial design. And so these were sacrificial nails. They're a little shorter than the standard nails typically. Some are long, some are just as long, some are shorter depending on what we're looking at. So you're looking at bond all the way along the nail. This is not a post-tensioned element. It's a passive reinforcement, and they're fully grouted. Here you see the shotcreting process. We go down lift by lift, 6 or 7 feet at a time if we can. Soil nails are drilled in, and then we apply reinforcing to the ground. You can see the Louisville soils here in the foreground. It's kind of a tan color, tannish yellow, and loess actually exists all around the world. 15% of the world has loess, some type of wind-blown silt on it. This loess came from the glacial age, Pleistocene age, when there were braided streams during the melt that really sort of ran down along the Mississippi River Valley, and then wind would blow the silt in the dry times and cover up a lot of the areas down the center of the U.S. So here you see this is our robotic arm for shotcreting. It's a very safe way to do it. It's a challenging process to do shotcrete properly, and it's not for the faint of heart, but this is the shotcreting process. And here you see we've gone vertical now for 2 lifts, and now we're coming out at that batter, the 20-degree batter, and drilling nails in and working our way down from the top down. At the bottom, this will be the location. You see these big PVC tubes. We're creating a void through that lower reinforced shotcrete beam, reaction beam, excuse me, using these PVCs. You also see the drainage. These are chimney drains that are placed in the rows between the soil nails to keep any hydrostatic pressure from building up behind the shotcrete. It's a watertight concrete system, and so this gathers the water so it won't come and build up behind the shotcrete. And then we put weep holes at the bottom, and then there will be a paved ditch at the bottom for the weep holes to drain into. Just another view here. You can see the change in angle in the wall from vertical to the 20-degree, and then prior to shotcreting, the reinforcement beam, and after shotcreting, but prior to the anchor drilling. And then we brought in a hydraulic track drill to drill these deep 150 plus anchors. We use strands for these to get to these high loads of almost 250 kips. And then the spacing varied depending on the design section, the height of the wall, et cetera, for these strand anchors from 6 to 10 feet center to center. There you see an uncoiler that we're uncoiling the strand anchor down the hole. It also includes a throwaway tremie tube that stays in there that we pump the cement grout from the bottom up. It's a 0.45 water cement ratio grout that hardens typically in the range of 8,000 or 9,000 PSI. Pretty strong. So we had a tricky outside corner. I don't know if you noticed in the plan view that I showed you earlier, And to deal with that, I like doing it radially. You know, some people try to drill, you know, crisscrossing anchors, but I've found through the years that radial support actually matches better the earth pressures applied, and works very well as far as avoiding interaction of drill holes. One of the things that happened here on this corner was, you know, you're trying to excavate around a corner, you're trying to keep a 20-degree angle, you know, it's pretty hard to do. And so we lost our 20-degree angle there, and it was noticed by our crew and the Army Corps people. And so we reported that back to our designers, and it actually decreased our factor of safety because you get a little bit more earth pressure load because you're not on that angle. So we had to add this extra row that you see the drill holes are in there around that corner to get our factor of safety back up. And the MSE wall was replaced at a slightly different location back from the bluff area and from the soil nail wall. We subcontracted that to a small contractor out of Mobile, Alabama. They did a great job. And then the wall was stained using a concrete stain to match the loess, and this is a picture here of us applying that stain. You also probably notice the bumps at every soil nail location. We do that for economy rather than using a lot of shotcrete to provide the necessary 3 inches of cover or so. We just bump it up around the bearing plates at those locations, and so this is called a bump wall, and that's what the bumps are all the way around. So at the end, we got to the bottom and we created an access road as required by the specifications. We put in a ditch to collect any water out of the weep holes, and then they were accumulated with pipes that ran underneath the access road and then were taken downhill with an elevated pipe structure at the low spots and put into gravel ditches to be drained down to the river. And there it is from a drone view all the way around. This isn't exactly at the end, but about the best shot I had. There's also a small MSE wall on the upper right-hand corner there to make the grade transition. So it's a very successful project. We love working with the Corps. They're good people. They're smart. They work hard, and so do we, and so it was a very successful project, and one that I'd love to do repeat work with repeat clients. So let's talk about another repeat job. This is a very recent project. It was on the news. I don't know if any of you heard it in the summer, but there was an unusual rainstorm that occurred in Wyoming near Jackson Hole, near Jackson, Wyoming. They got a tremendous amount of rain in just a very short period of time. There was a lot of water that came down out of the mountains due to that, accumulated in the valleys, and there were mudslides at a lot of different locations. And one of these mudslides occurred on June 7th, 2024, in between Victor, Idaho, and Wilson, Wyoming. And so Jackson Hole is a very expensive place. It's kind of a rich people's playground with skiing, very expensive rents, very expensive restaurants. And so unfortunately, the service people who service a lot of those restaurants and hotels, et cetera, can't afford to live there. And the rents are just too high. It's like, you know, $3,500 a month for a studio apartment, you know. And so a lot of them live in Idaho, and they make the commute every day back and forth to Jackson Hole. And they take Highway 22, which is in the valley or the pass, and it's called the Teton Pass. So when the mudslide occurred on the 7th, the road was fortunately closed because it was covered with mud, and then some of that water built up at a really high fill location closer to Wilson. Further down you see the mudslide was a little bit northwest of the landslide on the picture here, and a really big landslide occurred. in a place called the Big Fill, which is, was a 100-foot fill placed so that they could build Highway 22 through the mountain pass. The problem was there wasn't any good way to get around then for the people who had to get to work. And so it caused about a 3 times increase in their commute, or 2.5 hours, where they had to drive down from Idaho and go down to Alpine and go through the lower pass and then back up again. So the DOT was under tremendous pressure. They knew it was a big deal, and they had a very high average daily traffic on this road. So they were able to actually get a runaround road built in 3 weeks, which is incredible, but it wasn't up to standard, you know, of a regular road, but, and then begin the process of trying to get it fixed as soon as possible. And so it was only 3 weeks that folks had to do that bad commute. Some of them camped out down in Alpine and campgrounds, et cetera. It was a big deal. So the DOT put out a request for bids. We teamed with general contractor Ames Construction, and were able to fortunately get the job. We had a nice resume to submit to the DOT for our proposal with 2 previous landslide projects in western Wyoming. The first one was the Blue Trail slide that we did in 1997. It was a micropile and tieback wall system consisting actually of 3 different walls and some really big tieback anchors up to 18 strands because of high seismic requirement for the design. And that one went really well. And both these projects are actually in the Snake River Canyon. If you look on the map on your left there, the landslide is in the circle, and the Snake River canyon is down in the red dot there. The second project was shortly after Blue Trail. It was called the Elbow Slide, where the Snake River actually turns 90 degrees, known as the elbow. And that energy of the water going around that 90 degree ate into the slope and was causing many slides that had to road repair over and over again. And then we solved that one with 2 soil nail walls, one in a step fashion, one above the other, and then also built an MSE wall in front so they could actually widen the road in addition to repairing the slide. Sort of similar to what we did at the Natchez Bluff. This is the Blue Trail slide. The Snake River is a pretty wild looking river at that location. The slides would occur every year. You can see the scour that can happen with the snow melt down on the river, and it would trigger slides over and over again. When we were building this project, we found 40 feet of asphalt where the thing had basically been paved every year since the late 50s for cracking and settlement. And it was a very successful project, an innovative use of micropiles, and you can see a big drill rig hanging over on a crane at the bottom there to install the big anchors. But it was a very fun project, and one that had federally sponsored $100,000 of instrumentation back in 1997, and it's been through a lot. It's been through a couple of big earthquakes, it's been through a debris flow, and it's still there, so that was good. At the elbow, we had these 2 soil nail walls. The lower wall we buried, and you can't see it after we installed it, and then the upper wall we ran into a very short construction season due to the eagles nesting in this area. We weren't allowed to build while the fledgling eagles were in the nest. And so it ran over a winter. And this was actually our very first use of the mesh and geofabric system, a temporary steel mesh wall that lasted over the winter. And then this MSE wall was built the following year. But good work for good people, and they brought us back. This was our proposal. The DOTs are using a new concept that I was unaware of until recently called the CMGC process, Construction Management Manager General Contractor, where it's a 20-page proposal submission where you put in your qualifications, Some ballpark numbers. This was very quickly done between us and Ames. Only a month after the slide, we had this proposal in their hands. The way the CMGC works is you have a collaborative bunch of meetings with the owner, you develop a solution and a cost estimate, and then the final cost proposal is reviewed by an external independent cost estimator. So we were successful in getting this project with Ames. So let's talk about, okay, excuse me, first of all, not a bad place to work, okay? If you look here, we've got, the beautiful Teton Mountains, Jackson Lake, Jenny Lake, there's ski lodges, and so the job site was located in these areas. It was pretty funny, our guy who goes and gets the rooms for everybody, he goes out and he gets something in Wilson, Wyoming, where there were 3 restaurants, Burger King, McDonald's, and a gas station. And so our guys lasted for about 10 days, and they were in Jackson Hole, and then made the commute. So we were able to fortunately get Airbnb, so we didn't have to pay the ridiculous hotel fees. But we had lots of volunteers for this project. Let me just say that. So here is a photo from the DOT of the mudslide that closed the road, fortunately, that happened about a mile up from the big slide. And they had a precursor, some warning that there were going to be some problems here, and they had actually already installed an inclinometer and had just started to monitor it. But unfortunately, this rainstorm came in, and this is a video after the first big slide occurred. I'll just watch this here for a second. So there goes the inclinometer. So the road was closed, obviously, and then this is just another view. So they immediately began stripping the organics on the inside of the curb to and hired a contractor to build a runaround on a very tight and steep. You can see there the organics being stripped. They're getting ready to place 2 lanes on the inside of where this happened, and in the meantime, negotiating for a permanent fix. That's the guardrail hanging down there. But there was a patch at this location and more guardrail at the bottom there. You can see the guardrail coming down. So basically, you had this huge rain event. It caused where the lay of the land went from left to right there. It caused this mudslide to occur down below, but it supersaturated this 100-foot fill on the left-hand side here. And so they had a real high spike in the groundwater table, and that's what happened here. And then the yellow that you see here is the temporary detour that they were able to open in 3 weeks and help the commuters while we were getting ready and designing and mobilizing to put in the permanent fix. The permanent fix was designed by Wyoming DOT consultant out of Colorado called RJ Engineering. And the idea was a reinforced soil slope that consisted of lightweight fill. They had initially specified flowable fill, but there was no way to get a fluid material on this steep slope and to keep it there. And so Ames convinced them to go with a lightweight fill, in this case, a recycled glass material that was sourced from the East Coast. And so this is the design that RJ came up with. It was a 1.5 to 1 excavation in the fill itself in front of the detour. It's 100 feet deep to get to the geometry needed for the final pavement location. It was late in the year. This is at an elevation of like 7,800 feet, and so the snow flies early and it gets cold. and they specified temporary shoring by the contractor, that you see in the blue box here. We decided to go with soil nailing, and then in addition to the lightweight fill, there are some drainage layers that you see here on the bottom and up the side, the slope side, the excavation side, are drains, and this aggregate, this lightweight aggregate, is also free draining. So the whole idea is to get the water out of the slope, right? And there are also horizontal drains as part of this. And then RJ came up with a concept of 2 rows of micropiles, 2 rows of 2 micropiles that would act as pins on the bottom to get the factor of safety required up to an acceptable level. So it's a little hard to see here, but basically it was an L-shaped system of soil nailing. The soil nails, originally we had 599 nails, but the geometry worked out as built to be 583. They're 40 to 50 feet long. The side against the road, parallel to the road, was 410 feet long, and then the turnaround cutback was 115 feet long. We're 1 1/4 to 1 for the permanent slope and 1 to 1 for the temporary slope to end the wall that you see here. So 14 rows of soil nails. They were on vertical spacing of 7 feet. The maximum length was 50 feet long. So when we first designed it, the YDOT folks went out and drilled a bunch of borings, but they couldn't drill a boring at this location where the one is shown on the right here because the land was gone, right? And so that boring that's shown there was not a sampled boring, that was the inclinometer. And so they didn't do any sampling. All we had was a visual description of, silty sand, gravelly sand, and then weathered shale. And so nobody could find that log. So it was eventually found, but after the design had pretty much almost been complete. And so that, by taking that qualitative log and being a little conservative, it put a little bit of a hump in that red line there that is the weathered shale that you see there. Prior to that, our design went more, that line went on a much less steep angle. And so initially we thought the factor of safety was going to be much lower because that's a clay layer in there. And so we didn't know that the rock was actually going to hump up there a little bit. So that affected our design midway through. So you see here some design sections. This design was done for us by Burns Cooley Dennis out of Jackson. Our people were very busy at this time. And we came up with a back analysis to get the soil parameters for the final design by back calculating the failure, looking at the water levels, and we were also concerned that there was a residual, a layer of residual strength clay that was involved in this or created by this, and it's the dark stuff you see there. But that hump, you can actually see a line where the hump in the bedrock and the gray is there. That used to be yellow and was clay when we did the first design, and we got a factor of safety of like 0.9. But after you put that hump in, it was more like 1.15. But once again, that was a qualitative boring. We didn't really know what was there, and so we kind of hedged our bets. And back calculated the parameters and came up with a design with a final factor of safety of 1.31. And then on the far side, where we're cutting into the natural slope on a 1-to-1, we back calculated that. If we made that cut, it would be as low as 0.88 factor of safety. And so we designed our soil nailing there to provide a factor of safety of 1.3 as well. Okay, so in this case, we used a different type of soil nail, a hollow bar soil nail made by Ishabeck. This is a 40 millimeter diameter, 20 millimeter interior hollow bar that you can flush in place using weak cement grout. There's no actual drilling tool that you use. You put a throwaway bit on the end and you flush them in place using a wheat grout. When you get to the bottom, you pump thick grout, and it's a automatically grouted soil nail that you see here. So we had 2 different rigs here working 24/7, 4 crews, 7 days a week to try to beat the winter. And one of the masts was a 25-footer, the other one was a 14-footer that you see mounted on excavators. This is just a detail of the soil nail. It's they come in 3-meter sections. They have a coupler, and you flush them down to the required depth, which in this case was 40 to 50 feet, and leave that bit in the ground and pump them up with grout. And in this case, we decided not to use a shotcrete facing. We were in a hurry, and it was going to be cold, and we came up with this soil nail facing that consists of a geotextile with welded wire fabric over it. Those welded wire fabrics are attached together with high-strength hog rings and aligned with tie wire. And then in between the individual nails, we create a wale using horizontal number 7 bars that go underneath the bearing plates that are 12 inches square. So this is a fast way to do temporary soil nail facing. This is just a detail of that. You see the horizontal bars from nail to nail. Excuse me, the details of the W4x4, 4x4 mesh. It's a high strength mesh, and it's, keeps the soil filtered underneath with a non-woven filter fabric. The step process shown here from 1 to 5 is you place the geotextile, hammer it with some big nails against the sloping surface, which is on a 1 1/4 to 1. You put the mesh sheets in place. They're secured at the locations where the soil nails stick out. We tie the wire mesh sections together. We place the wale beam from nail to nail as shown here, and then put the bearing plates on the nails with a beveled washer and a nut and tighten them down. So pretty simple and very effective. The excavation was done by the general contractor Ames 24/7. They used a conveyor belt to get the soil out, a very long series of conveyors. They had 3 excavators and a dozer to move the soil, and they were always moving soil 24 hours a day. It was a large earth-moving project. We also did the test nails as described in the Natchez, 1 per lift. That's the blue bar you see there. That's a protective PVC while we're building the facing, and went in and ran pull-out tests. We got good pull-out in this rocky fill material. This is just a setup of the pull-out. We basically do a pull-out test at 2 times the design load. We run a creep test at 1.5 times the design load, and it's the same type of Post-Tensioning Institute specifications that you see on anchors, very similar, and this is our soil nail pull-out software and graphical representation to make sure that we pass our tests. So there she is. It's a big wall. We did it in 5 weeks, 60,000 square feet. It was a tremendous effort of our crews, and we're very proud of them for that. Big wall. So then, as part of the final design, Ames hired a specialty contractor out of Oregon called Jensen Drilling to do horizontal drains. There were 5 drains required, drilled 90 feet from the bottom of the soil nail wall into the backfill and the natural materials that are shown here in the blue lines. The blue line that is across the bottom there is the bottom edge of the soil nail wall. And then they would extend those drains through the new fill being placed out to the outside of the final wall. So there you see the location of the drilled nails in the blue line there. That they were 90 feet, drilled 2-inch diameter slotted pipe, and on a 5-degree upward angle. It's hard to see here, I don't have any really good pictures, but Jensen uses a funny rig called the Aardvark. It's a Caterpillar D4, and the drill mass is actually mounted on the side of it, and it drills at very low angles. And so if you look real hard at the bottom, you can see an aardvark right down here and over here, right down over here and down here. That's the aardvark, and it's a very effective drill for low angle drilling, and they're very good at it. Then, as I mentioned earlier, as designed by RJ, were these permanent slope stability micropiles. There were 140 of them. They were 50 feet long. They consisted of 9 5/8 inch outer diameter pipe and an interior 75 KSI bar, full length. The pipes were 35 feet and a 15-foot rock socket. When we first started drilling these, we encountered some very soft clay materials that were highly plastic in the drill cuttings that were a matter of concern because of the earlier time when we thought, hey, I wonder if there's some residual material here from the slide, or is it natural, et cetera. And so that was a concern. Here you see the locations of the 4 micropiles. We left 8 feet of pipe sticking up out of the ground. We were determined to do further investigation into that clay, and had a series of meetings. Here you see the layout of the micropiles and the location of the lightweight foamed glass aggregate backfill. There are layers of biaxial geogrid that run the horizontal lines that you see there. So here's the layout of each one of the micropile caps that you see here is a 4-foot by 5-foot reinforced concrete cap. The micropiles were spaced in pairs, 10-foot center to center with 15-foot rock sockets. And so we dug some test pits, and you can see on the lower left-hand side there, on the right-hand side, there's a white clay-looking thing. It was like a montmorillonite that was either a myelinite or a gouge, fault gouge or something. It was very isolated. And so we dug 5 test pits all along, and that was the only location, was right where we were drilling the micropiles. And so it was a false alarm, so that was good. Here you just see some construction pictures of the micropiles. We had 2 drill rigs, brought in a new superintendent who was a micropile specialist. We ran 3 tension tests. The design load was only 55 kips, 110 kip test load. We ran those tests in tension. And there you see the permanent slope stability micropiles. We completed that work in 3 weeks with 2 crews, 2 rigs, working 1 long shift 6 days a week. And when we left the site, Ames had already started placing the gravel blanket for the drainage on the bottom of the fill and starting to cast the micropile cap, as you see here with the formwork. And they started hauling in the lightweight aggregate fill, but very shortly thereafter, everything turned white. And you can see on the right-hand side, our wall, that's where our wall is all white there. It started snowing. And so they fought the good fight as long as they could in December and got about a quarter of the wall in, and then things just went to heck. And we got tremendous snowfalls, minus 10-degree Fahrenheit temperatures, et cetera. And so we're now waiting for the spring thaw, and they will finish it at that time. So I've got a few acknowledgments. I'd really like to thank Jesus Trado, who was the project manager on both these projects. Vice Presidents Joe Cavey and Ryan Smith, a great site engineer, Jose Areza, who did a lot of the PowerPoint for me here, and then we had Michael Caprero do a really nice fix-up of all that and make it very professional. So superintendents were Miguel Castillo, Luis Ibarra, Donnie Cupstead, and Chris Richardson was the superintendent on the micropiles. And I'd like to always thank Brad Campbell and Alex Reeb, Burns Cooley Dennis, Cole Murray and Rob Wise were at Ames, and James Dayhill is the chief engineering geologist at WYDOT. He was a young field engineer when I started working with him at Blue Trail Slide, and now he's the boss. So I want to thank you very much for the opportunity. This has been great. Thank you, ASCE. Thank you, Geo-Institute, and cheers. Thank you.